Okay, hey, welcome to Lecture 7 or Lesson 7 or Topic 7, whatever we want to call it. Thanks for the great session at COSI on Thursday. I thought that was really great and look forward to the rest of the course. This comes kind of out of the discussion. I think we decided that resistance, electricity, and so forth were a good topic for moving forward, so that's what this will be. And that's the main topic. What happens when you light a bulb is basically what we'll go through. Before I do that, I want to, as we typically do, talk about what happened last time. And again, I think I went a little too far with the phase diagram thing. It isn't so bad, but just 1 hour, and it is out of context. It probably doesn't quite belong in the ninth grade. But at the same time, it does make the really some nice points about that this idea of mixtures, solutions, and what the structure of solids looks like, particularly after you get through atoms. We could do a nice job of that, and it all relates back to this. And as was brought up in the discussion, the fact that salt segregates out of ice is something that has saved lives when people try to drink in the Arctic. And also this eutectic is something that allows you to cast at lower temperatures, and that's a trick that's been used also back from many, many years ago. So again, watch the phase diagram lectures. There's other good content out there. I'm not going to spend too much time on this, but let's go through the questions that I posed. For A, I said you're at 57% bismuth by weight. This is by weight or by mass. I should probably say by mass myself. What structure do you expect at 140 degrees C and 135 degrees C? So 140 degrees C. So this was chosen. So this is 57% here. Is what's called out. Here's 139 here. So the idea was 140 is just above this, and this is just below this. And so what we're looking for is just above. This is all liquid. And if you get just a few degrees below this, this is a mixture of two solids. A tin-rich solid with that composition and a bismuth-rich composition that has almost no tin in it. It's a lot like water excluding salt when it forms ice. You have almost no tin in the bismuth-rich solution. And you would get this eutectic structure. So just below this, you've got a microstructure that would be sort of plates of bismuth and plates of tin, and that's what you would end up seeing, and these would be the solutions. And this being about halfway in between, it'll be about half and half bismuth-rich and tin-rich materials. Okay. Part B, I asked what are the types and approximate compositions of the phases. You would see at 30% bismuth, so 30% held at 150 degrees C, so 30%, 150, would be a point right there. And what you would see is a tin-rich solid of that composition in equilibrium with a liquid of that composition, and you would have a little bit more solid than liquid because this is closer to that. And so the microstructure in part B would be these kind of tin-rich blobs in a liquid that would have this composition that's about 50-50. And there would be maybe about 2/3 solid, 1/3 liquid. And again, you can read all that stuff off of the phase diagram. That's not the point of this lecture, so that was the point of last lecture. And again, I think it's a little bit too much. I'm learning to. We'll get there. This time, I think this is stuff that will. Today, I think will be stuff that you'll find useful. So, with project update, I mentioned that some of the points, enough points to bring you to 100%, come from the project. And I'm really, if everybody's sort of in good standing, have hung with all the lessons and responded each week, and you do some sort of a project, that will get you an A, and we'll fudge the numbers to make sure that works if we have to. Here's what I want to do. Again, I want to do things that are really of value to you guys and long-term value for this process. So what I'm hoping to do is ask you a question. How do you use material science in your classroom? Hopefully you are or can. And the due date is something like something like April 20th. We have to close down. I don't know exactly when it is. The last week of April is the last week of our spring semester. So we have a fair bit of time. Hopefully you do use material science. Describe to me how you do. If you can provide a lesson plan, that would be great. If you do a lesson, I'd like to see some how the students respond and include some example work with that. And then I want you to sit back based on what you've learned through material science in the summer, through this course, through the interaction, through what you're doing in your projects. Think about what you can do to improve upon it. And it could be, if this is the same project you're doing for MSP at COSI and what you're doing, you'll be presenting in a few weeks, that's all the better. I don't want to put any extra burden on you. And if you don't have anything, propose another similar sort of project. It could be hypothetical on something you might like to do next time, where you might make a lesson plan, talk about how you might use it. That would be fine as well. Again, I want to leverage what you're doing and not add busy work. Don't. It's not the point. Okay. So that's that. Let's go on to the topics today. Learning objectives for this exercise. First of all, what I'm hoping you will be able to do is teach Ohm's law, which is basically V is equal to IR. We'll get to that to your students in a compelling way where they actually understand what this means. And again, math is the language of science, and I really think if we can get that point across and show how powerful and really predictive math can be, it will blow the students away, and it still actually blows me away a lot of times how much we can predict things. We can describe resistivity as a material's property, and then we'll also have several open-ended activities that you can deploy. We'll point you towards some examples you can use, and we are going to use a light bulb. This is one that the material science camp, and I think Andy Neidham had a lot to do with this, has been using for many years, and it's a great demo. I've used this in front of some classrooms. It works really, really, really well, and we'll put you towards some resources and give you some ideas. And again, could do days on this, and I think in your classroom you can expand this to hours, but we'll hopefully finish this, no more than half an hour from now, I hope. So where does this fit within the existing physical science timeline? And again, the new one isn't going to be so different, but if you can actually read this, you get to middle of or end of grading period 2. Electrical conductivity of different materials, role of electrons. Light is a wave, so it is absolutely core right there. Energy transformations, this is core in. We're going to be doing energy transformations directly. Motion, sort of. Classification of matter, this also works with. We can also bring in aspects of atoms and periodic table and so forth. And just by the way, if it were up to me, the atomic postulate would be right up front, so we could build upon it rather than do these things without atoms and then bring the atoms in later. But we can do it either way. But I think there is a lot to be built on there. Just my personal opinion. Ohm's law is this, and there's a nice water example for this. And Ohm's law is basically V is equal to I, R, or V is voltage, really voltage difference across some circuit. I is current, and R is equal to resistance. And the thing that you have to realize is it always has to act for a circuit. So the electrons or the current, call it electrons for now, must kind of what I would say return to home. You can't build up charge somewhere. It has to be a current. It has to be a closed circuit somehow. And that's where this water analogy sometimes fails sometimes. But a lot of people see this as a water analogy. If you've got a water tower, a picture I stole from Wikipedia from Wauwatosa, probably Wisconsin or Minnesota, sounds like one of those places. Based on the height of this, that gives you a pressure. Basically, all that water pushes down on the water that's beneath it, gives you a pressure, and that's where you get good water pressure. That's why you want this to be up high. If you've got a house up higher than that, you're not going to get water. And then that pressure basically is what causes flow. And then you might have something like a valve in here. And as you open that valve, you get some kind of flow rate. And the greater the pressure at the given valve setting, the more the flow rate's going to be, or the more you open up the valve, the more that flow is going to be. So the other way you could write Ohm's law here is you could say the current, I, is equal to voltage divided by resistance. So in the water analogy, what you have is the higher the pressure or the voltage, or then the lower the resistance, the more you open the valve. Opening the valve is lowering resistance, the greater your current will be. And that's basically Ohm's law. I'm not sure if you do that in ninth grade. I think that's simply something you certainly can do, and I'll assume we can. And we'll go forward from there. So let's consider these pieces within Ohm's law, and these are basically pulled standard Wikipedia sorts of definitions off of this. V is voltage. Sometimes you'll make it delta V, which we often call a potential difference. This really is a potential energy thing. So the volt is this SI unit of electromotive force, force on electrons, where the difference in potential, a potential difference that would carry 1 amp of current against 1 ohm of resistance. Okay, so there's a little bit recursive definitions here. We carry 1 ampere, usually called amp, of current against 1 ohm resistance. So it's a linear relationship, and basically it says voltage and is basically it carries 1 amp against 1 ohm. Okay, and that's it. So if the resistance is higher, the voltage is higher at the same current, or and you kind of get the thing. That product gives you voltage. Okay, and we'll do the math a few times as we go through. Let's not dwell on that. Current, I, is basically how fast the electrons flow. This is the SI base unit for electrical current, is the ampere, or amp, as I usually call it, and is equal to the flow of 1 coulomb of charge per second. This is 6 times 10^23 electrons per second. And I should triple check that, but I'm almost certain that's true. I'll issue a retraction, but it's a mole of electrons per second. And actually, what I'm no, keep going from there. So that's basically that. And then R is resistance. It's the electrical resistance of an electrical conductor is the opposition to the passage of electrical current through a conductor. Electrical resistance shares some conceptual parallels with the notion of friction, meaning that it's something that often damps things out. It's a way energy is absorbed, much like friction can absorb mechanical work. Resistance can absorb electrical work. The SI unit is the ohm, and basically that's so we can say that R is equal to, let's say, V is equal to I R, or R then is equal to V over I. So that's resistance. So if you need a large voltage to get a current, that's resistance. Then we have conductivity is 1 over resistance. We typically don't talk about conductivity too much. We usually talk about resistance of elements, But there is a place we talk about conductivity a fair bit, and that's when we compare metals to one another. And here's the conductivity of a few metals. This is copper is the standard. Always we make electrical conductors. I shouldn't say almost always. Commonly, for household wiring and all that, we usually make our conductors out of copper. This is a conductivity of 100. It's our baseline. There are some materials like silver that isn't shown on the list here, has a little bit higher conductivity, something like a 103 or 104 on this scale. And then these are basically numbers how conductivity compares as a fraction of the conductivity of copper. If you make an alloy, you really reduce the conductivity. Pure copper is a better conductor than copper alloys. Copper alloys can be stronger. Pure aluminum is down here about 59. Aluminum alloys down here usually between maybe 30 and 55 or so. Brasses, which are largely copper alloys, are fairly low. Steels can be quite a bit lower. Stainless steels can be much lower. Titanium is much lower. You see titanium's on the list twice. And so you're seeing the range. Copper is good. A lot of other things are not nearly as good. So if you're going to make wiring from your house, we'll see that conductivity matters quite a bit. And we'll consider exactly how it matters, and we'll come back to this, or you're free to come back to this later on. So I'm just going to put a bunch of data out here, and we're going to come back to this. Here's a bunch of materials here, and here's the other unit, and we'll deal with this unit in a little bit. Resistivity in terms of ohm meters, and this is on scale, so writing this number out is basically 1.6 times 10 to the minus 8 ohm meters is the resistivity of copper, and that's what that shorthand means. Just look at this column for a moment. Here we've got a bunch of things, and maybe just look at the things here. These are all metals. Nichrome is a metal. And stop there. Glassy carbon isn't. Copper would sit here at 100 and yield copper. And you can see that these are all of largely similar order. These go from 10 to the minus 8 to 10 to the minus 6. And if I turn this into conductivities, and this is this number we talked about in the last slide, this IACS, and I should define that term. This is what's called the International Annealed Copper Standard. And that's basically, we just compare the conductivity of metals as a fraction of that of copper multiplied by 100. So here they are in these kind of difficult units, and here they are in these IACS units over here. And you can see metals are all, sorry, let me stop there. Metals are all, between 1 and 100, sort of. They're all pretty conductive. If I go to other materials also kind of conduct, but not nearly so well. Carbon is a fairly good conductor for a non-metal, but it doesn't even show on this scale. It's 2 orders of magnitude lower than that for nichrome, which is one of the least conductive metals that we have. If we get to seawater, it's even lower, about 10,000 times less conductive. You get to glass or air, these things are much less conductive yet. So these things, while they still have some conductivity, they're completely different. And you can tie this back to how electrons move through the solids. In these metals, electrons move relatively easily. In these things, electrons don't really move. Here you can move ions. Here you can kind of move some electrons a little bit. If you deionize the water, you don't even have ions to move, so your conductivity goes up by a factor of 1,000. Glass, air, Teflon, there are no free electrons around. So there's big differences, huge differences between metals and these other things, and there's even big differences within metals. Okay, so we'll come back to this, and what's kind of nice is, remember from early on we have already copper wire, got aluminum wire, we've got stainless steel wire, we can get nichrome wire, we don't have that right now. We could get nickel wire, and so we can do some nice things with the wires that we have, and I think if we make those a common piece in our physical science kit, there's some cool things to be done here. Okay. Hopefully you're bearing with me. It's always better to do these things in front of an audience. So anyway, here's some primary definitions. Wikipedia, as usual. Superconductors truly have no resistivity. Superconductors I don't think any exist at room temperature. Used to have to go down to pretty darn close to absolute zero, but we don't anymore. Metals in this range about 10 to the minus 8. Semiconductors, electrolytes variable, much lower. Insulators are orders and orders of magnitude higher. So you're looking a difference of on the order of 20 orders of magnitude. So they're completely different. It's true that insulators can conduct a little bit of electricity, but very, 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 very little. Okay, so let me go back and let's talk about Ohm's law again. And Ohm's law basically says V is equal to IR. We talked a little bit about what each one is. We often can put these in sketches like this where we talk about voltage. We usually use a battery or a little symbol for battery. Might look like this. You've got a long plate and a short plate that might look like a cell and a battery. This is a positive electrode. This is a negative electrode. When we've got current, we say that current flows from positive to negative. So what we would have is we make a circuit out of this and allow the current to flow like that. We've got to complete that with a circuit. We would say that the current would be flowing this way, like that, flowing from positive to negative. But, and that's just our definition of current, but really electrons flow the other direction. Electrons flow from negative to positive. Okay? So if I did this, if I just took this and put a wire here with very little resistance, this thing would probably short itself out. You'd have a very high current. This would heat up in a hurry. So we usually stop this by putting a resistor in there. And a resistor we usually use as a squiggly line as sort of the standard way that's done. And that's your resistance in like that. Okay, so if I make resistors in series, I can do something like that. And basically, let me erase this so I've got a little room. So let's imagine I've got resistors. I can go to Radio Shack and buy resistors if resistors as I like. And let's imagine I've got a battery here. And let's say that this thing puts out 7 volts. Okay? And I'll take this thing and I'll say this thing goes across 3 resistors. R1, R2, and R3. Goes back up like that. Again, makes a complete path. R1, R2, and R3. So what has to happen is the current always has to be the same everywhere. So we're going from the positive side to the minus side. Current goes around like that. And let's say R1 is equal to 1 ohm, and we use this omega symbol for ohm. R2 is equal to 2 ohms, and R3 is equal, say, to 4 ohms, like that. Okay, so what has to happen through this is the current has to get home. The current can't just wander off anywhere. It has to. If you have a current circuit like this, what leaves here has to end up back here. And so the current that runs through R1 has to be the same as the current that runs through R2, has to be the same as the current that runs through R3. So that's that statement there. So I could take a voltmeter And this is something I would encourage you to do in your class. And all you could do is, if you have wires exposed, this is, if you're using low voltages like 7 volts, you can do this just where you have a voltmeter like this. And I could clip that voltmeter from here to here. And across these good wires, these are good conductors, ideally zero resistance. I would see no potential difference between here and here. Okay. So now, let's take for faith that the total resistance is equal to the sum of R1, R2, and R3. So if R1 is 1 ohm, 2 is 2 ohms, 3 is 4 ohms, add those up, R subtotal is 7 ohms. Okay, so what would, let's take this on faith and we'll go back and understand it. What would the current that runs through the system be? Well, V is equal to IR, or I is equal to V over R. Well, V is 7 volts, R is 7 ohms. That means I've got 7 amps, or I'm sorry, 1 amp runs through the system. And so I've got I here going this way. I is equal to 1 amp going through this thing. I'm just going to make a little room here. So now what I could do is take my voltmeter and say put it across R2. R2 has 2 ohms across it, and if I clip it between there and there, well, what should my reading be? Well, if a current of 1 ohm is running through there, R2 is, if a current of 1 amp is running through there, this is a 2 ohm resistor. Voltage I should measure here will be equal to 2 volts. So if I take one part of my voltmeter, clip it there, and then imagine the other part could clip somewhere along the circuit, the voltage I would measure as I go across would go from 0. As I pass R1, it would go to 1 volt. As I passed R2, it would be 1 plus 2 more would go up to 3. And then when I pass R3, it would go up to 4. And this would be 7 volts here. This would be 3, and this would be 1. So I could take my voltmeter, clip it here, it'd be 0. Here it would be 1. There would be 3. And there I'd have the full 7, which would persist anywhere I'd put the clip all the way up to there. So you could use a voltmeter, and again, voltmeters, you can go to Harbor Freight and get a very, very nice one for about 20 bucks. And if you deal with voltages that are under 12 volts or so, there is no safety hazard in your classroom. Have fun and do real science. Teach them to be real scientists. Teach them how science and measurements and all this and math all fit together. So if we do resistors in parallel, I can do the same thing. And now what I'm doing is I can have my battery look like this. Again, let's imagine it's 7 volts. And let's say I got 3 resistors. R1 is equal to 1 ohm. R2 is equal to 2 ohms. R3 is equal to 4 ohms. Now what I'm going to do is I could take a voltmeter, put it anywhere across here, measure the potential difference across these, and I'd have 0 potential difference. This is all at higher potential. This is all at lower potential. This is positive. This is minus. There's a 7 volt difference across here and here. So if I've got a 7 volt difference going across this, across say a 1 ohm resistor, what will I get here? I'll get I here is equal to 7 amps. I across R2 would be 7 over 2, or 3.5 amps. And then if I had R3 where it's 4, put it as 1 and change or so is our current that runs across that. So by putting the resistors in parallel, but putting them so that you have the voltage running across all of them at once, you see a much higher total current than you would in the other case. And if you work out the math for this, which probably goes beyond where you go 1 over R total is equal to 1 over R1 plus 1 over R2 plus 1 over R3. So you can do an equivalent circuit that way. Okay, and I'm not going to go into that. That's fairly simple. If you go to lots of places cover this. This is Google this in Wikipedia, do parallel versus series, and it comes right up. But this is a thing. So in summary, you can have current running through resistors in series, or you can have it running through parallel. And the big thing is that the total potential that you put on the circuit has to be the sum of the potential drops across each of the resistors if you have things in series, and then R for the equivalent circuit is R1 plus R2 plus R3, etc. And then if you have things in parallel, you've got the same potential that runs across all of these, and you have the same voltage drop across each, and then the total current would be the sum of the currents that go through each of these guys. Okay, so that's parallel, and we'll come back to this in sort of a abstract way when we get to wires in a minute. Okay, so this is all really, really good stuff so far. What I don't like about it, and I probably should have pulled up a picture. If you go to Radio Shack, you can buy resistors, and they look like little pieces of carbon. And they look like that, and they've got these little bands on them. If you know how to read the bands, if you're a bit of an uber geek, you can look at the colors on the bands and say, "Oh, that's a 3 ohm resistor, and it's a high precision one." You don't want to go there. Instead, what we would like to do, or I'd like to do, is use wires. We have already introduced the topic of wires. We can get wires in many different materials, including aluminum, copper, stainless steel, I think that's stainless, brass, high-strength steel, nichrome, tungsten. Tungsten's a little hard to get, possible. And you could also get rubber or nylon, and good luck conducting anything through nylon. You'll find it doesn't work at all, even though on paper it shows some really small conductivity. So now what we can do is use wire and make our own resistors, and you can either make a resistor simply by a straight piece of wire, or if you want to be compact about it, you can make a spring and make a wire and make a resistor like that. And so long as you don't make it so it's all tangly, so that you're conducting along the spring, you can make a really nice resistor that way. And we can actually pick any resistance we want and get that. Well, how do we do that? So resistance of a wire, R, is equal to the resistivity, and this is in ohm meters, times length, which is in meters, divided by area, which would be pi r squared, where r is in meters. And put the square on the outside just to. So what do we get out of this? We get, this would be meters squared down here, so that cancels with that, and you're left with ohms. So all you have to do is, if you're careful with your units, do everything in meters, for example, get your resistivity, know your length, know your cross-sectional area, and you can calculate the resistance of a piece of wire. And going backwards to what we had before, we've got three primary variables we can change. One is what material we pick, and we can see within metals alone, there's almost a factor of 100 over the resistivity of wires. The other thing we can pick is the length of it, and shape doesn't matter. We can make it into a coil, and we can pick the cross section just by, again, going to MasterCar. I've got all kinds of cross sections I can buy. Okay, so that's what we can do. So we can use wire. Wire makes great and transparent Okay, so I advocate using wire in all of this. So again, you can go and commercially, people have thought this through tremendously. And there's this thing called American wire gauge. The higher the American wire gauge is, the finer the cross section is. So at the bottom of it is like these zero gauge. So like a zero gauge wire is 0.3 inch diameter. You don't want to get hit with that, and that is something that you might end up carrying. Well, you look at resistance. You can look at the resistance of this thing in terms of ohms per 1,000 feet. You know, it's a very small fraction of an ohm per 1,000 feet for a wire like that. And you can carry with a big thick wire like that and keep your insulation very cool. 125 amps. You can carry thousands of amps with it before it vaporizes. That's that fusing current. And that's for really big wire, and this is what you'd see for powering buildings and such. But much more interesting for the classroom is stuff you can buy very cheaply down here. And these are wires, the 40 gauge wire. You can buy from McMaster Carr, get a spool fairly cheap. This has a diameter about 70 microns, 80 microns, so you can easily break it. Again, we can use that for strength testing. It has a cross-sectional area of 0.005 millimeters squared. And this has interesting resistance. So for 1,000 feet of this wire, so this is ohms, here, milliohms per meter. So it says 3,000 milliohms per meter, so that's something on the order of 3 ohms per meter of wire. So we can use this fine copper wire. And be careful not to put too much juice through it, because at 2 amps at about 10 seconds you're going to end up melting the wire. But that's actually a good thing. It limits your students as to what they can do with it. So so you can, again, even with copper, you can do that. Or you can change to stainless steel or other things that have higher intrinsic resistances to them. Again, 40 gauge copper wire. I've got a big spool, very happy to share. I think $20 buys you about a mile or two of wire. It's little money goes a long way with that. So we're not by any means the first people to talk about measuring resistance of wire. This is something from Cambridge that's online. Basically, you can do this two ways. You can either buy a commercial ohm meter, go to Harbor Freight, get an ohm meter that basically has all of this in this, or you can take a battery with an ammeter and a voltmeter, which basically makes an ohm meter. And what you end up doing is, this is the wire that you're interested in testing. Couple the lead to one side, measure from the voltmeter on the other side, and you'll find that as you go down here, you see a much higher voltage, closer. Actually, both voltage and ampage will change depending on how you do this. You'll see these readings change, and you can figure out what the resistance is. Resistance is, I always have to do this, V equals IR, so resistance is voltage over current. You can measure those two things and come up with that. Or what you can do is just basically take your wire, take a long enough lead of it, and put an ohm meter across the two ends and measure that, and that's probably more likely what you would want to do. The trouble with simple ohm meters is usually there's some contact resistance that's on the order of a half an ohm usually, or so, and usually the first half of ohm isn't always so accurate. So the other thing you can do with this is you could put a known current through here, and if you have some contact resistance, you could do that, and then just measure the voltage across any 2 points on this. And if you know the distance between those 2 points, you know what I is. because you measured that here. You know what voltage is, so you could figure out what the resistivity is of the wire that's in between here. It might be a little complicated. I'm sure if you want to, you'll figure that out. So a possible easy lab you can do is just have a bunch of wire around, give them the table, give them the equations, and a lab can be I need a 15 ohm resistor from wire. Here you've got these boxes of wire. First group to get between say 12 to 17 ohms wins. So basically each group has some time to measure wire, figure out what would do that, do the computations, and then just put it on the ohm meter, see who wins, see who gets it. Every time you'll get a reading. It's extremely safe, and that's a very, very easy thing to do that I think would be good, and I think contests, having winners, is always a good thing. The other thing you can do is look at energy dissipation. That's what I want to turn to next a little bit. And how do you do energy dissipation, play with electricity in a classroom setting? Well, these are things that we've got all over our house from things that we buy and throw out. I usually end up saving the chargers. And if you just read what it says on these things, you can see how they're immediately useful. You can see that the output for this thing is, in this case, 12 volts, which is kind of a nice level. It's large enough that it's meaningful, but it's small enough that you can't hurt yourself, and you can't go beyond about 800 milliamps, about 0.8 amps, and this gives you 9.6 watts of output. So based on that, if you don't want to go beyond 800 milliamps, well, if you have so if 12 volts, if you've got a 24 ohm resistor, you're going to be at half an amp. So you want to have a resistance, somewhere in 20 ohms or thereabouts, or you're going to burn out your power supply, and it won't be very dramatic if you do. I'm pretty sure there's a little fuse inside. It'd be a piece of junk if you do that. So you can just say, okay, we're going to class, we have this power supply. Hopefully we don't wreck it. Give me a resistor that's 20 ohms or better. And so you can calculate how much resistance you need to be safe at 800 milliamps. And then what you could also do then is take off of this, cut this end off, connect to the end of this. You'll have most of these, let's see, does it show? Yeah, it shows you also that your inner conductor, for what matters, is positive. The outer is negative. That's what it shows you right there. So you could either work off of that, or you could cut the end off and put alligator clips on it if you like. Then what you could do is take this thing and instrument it. So you've got for example, a styrofoam cup of water. Put into this, say, 100 milliliters of water. And you've got your power supply, and then just put a cable and a coil inside of this. Bring that back out, and what will happen? Well, you turn the power on. Well, first of all, where's the electricity going to go? Is it going to go primarily through the water or through the wire? You can answer that by just looking at conductivities, and you see that the conductivity of the wire is much, much higher than that of the water. So while a little current might bleed through the water, most of it's going to go through the wire. And what you can also do then is measure the current that goes through this thing, the ammeter, and then separately measure the voltage across here. And if anybody wants to talk to me on exactly how you instrument that, I'd be happy to talk you through it. And by knowing what the voltage and amperage, you can know what the power is. And the rate of power is basically the voltage times the current, both of which can be measured. Where does that power go? That power turns into heat. And 1 watt of heat is basically a volt times an amp. So you know how many volts, how many amps are you going to be at? 12 volts, you're going to be something like on the order of half an amp. So you're going to be doing something like 6 watts. This thing can't go beyond 9 watts. And water heats up 1 milliliter of water heats up 1 degree C based on 1 joule. A joule is a watt second. So you can actually see that the water heats up at a rate linear to this. And you can put in different coils and see that see which coils end up heating your water up faster. Okay, so there's a really nice lab that could be developed in there simply by showing energy dissipation, heating water, and the rate at which the water heats is going to be proportional to volts times amps. There's ways you could do graphing lessons in there, measure the temperature of the water every minute, and then see how that depends on V and A that's going through there, for example. And these things, again, all over the place, cheap. I've got at least 10 discarded of these guys in my house. Easy to find. They're all over the place, and they're all they're also all different. This is a fairly low power one. If you get something like from a computer charger, those are usually 45 watts. You know, this one is only 10 watts, and you can get them all over the place. So we can do power dissipation. If we use V over IR as Ohm's law, power is voltage times current, and then you can say that current is voltage over resistance. So we've got 2 expressions we could use for power. Power you can take as I squared R. If you measure current and you know resistance, you can get power that way. Or if you have voltage constrained, you know resistance, it's voltage squared divided by resistance. Okay, I'm just going to leave those there. They're fairly simple. This is the fundamental equation for power. The others are derived from it. And leave that for there. You can come back to that if you like. So now, what you can say is imagine we've got a power plant over here. Imagine I got a power plant. It's got some smokestacks associated with it. Power plant with smokestacks. Off of this thing, I get my power lines. Imagine these are telephone power poles. And I'm here at my house, and I want to light my light bulb here. And imagine I've got a light bulb that I want it. And so the power comes from the power plant all the way to my light bulb. We know that the light bulb, in order to light, say this thing needs, say it needs 3 amps to light. How much loss will there be from the power plant to my light bulb? Well, we know that 3 amps basically has to come the whole way from the power plant to my light bulb. So what's the loss? What's the loss in transmission? Well, basically, power is equal to voltage times current. My current is 3 amps, and I know from here to here, if I could put a voltmeter across it, I'd have some voltage across those power lines that I could measure. That's a voltage drop. That's this voltage from that 3 amps. So I know what my 3 amps are. I can say V is equal to IR. Well, what's the resistance here? Resistance is basically the conductivity of my lines times their length divided by their area. So basically, this is going to be 3 amps. My losses are proportional to the resistance of my power lines. So this is, again, deeper than you want to go with 9th graders, I know, but I think you might be able to get them there. So the question I want to ask is what makes a good power line? 3 things. You want it to be short, You want it to be fat, and you want it to have high conductivity. So the high conductivity, this is why we use copper. We could use silver. It's a little bit better, but an aluminum is actually quite a bit worse. Sometimes we use aluminum. And you want it to be short. You want to be close to the power station. You can't always do that. We don't like power stations in our backyard. You also like those conductors to be fat. But why? And so we make them fairly thick, but we don't want them to be too thick because we're putting a lot of money into copper wire, and you know people steal copper wire as it is. So there's a real engineering trade-off that goes on here. We lose electricity just through the power lines because it would really be better if we had fatter power cables or we had the power closer to us. So there's actually some really interesting environmental trade-offs that come out with all of that. Okay, so let's continue that analogy a little bit further, and let's focus now on this part of it, the light bulb. Say I've got my voltage coming in, I got current, I want to use it to light a light bulb. What does a light bulb look like? A light bulb is really amazing. They think that Watson and Crick developed double helix. Well, really, the light bulb guys did. This is what a light bulb filament looks like. This is tungsten wire. Put the W first to make tungsten. Wire of tungsten, and you can see it's coiled up like this. But then those coils are coiled up like that in sort of a double helix structure. It's basically you can get a lot of wire, get a lot of resistance over a short distance, and that's tungsten. And they're going to put across that filament not a few volts, but you're going to take over these filaments where you've got long distances of wire. You're going to put 110 volts across that wire, and you're going to get some current that runs through that thing, and you're going to get that thing, so you're going to get it hot enough so it glows, and that's that was Edison's discovery of way back when, and a very tricky thing, changed the world, and so that's basically the essence of it. So you got a tungsten wire, you're going to run enough current through it so you dissipate a lot of power, it glows, and this is all material science. It's really, really good. So first question you should know is which will have a greater resistance. So 40 watt, 60 watt, or 100 watt bulb. And again, if you have an ohm meter, you can measure this thing, and you will find, I'll give you a second to think about it. Actually gave you the answer a little while ago. I'll just go back a little bit. Here's the equation that gives it to you. You've got voltage fixed, power, which is measured in watts, is equal voltage squared divided by resistance. So roughly a 50 watt light bulb should have twice the resistance of a 100 watt light bulb. You're letting more current go through, and the voltage is always about 110 volts either way. So bigger light bulbs have lower resistance associated with them. So this one has lowest resistance. That means highest current, most energy dissipated. And you can measure that, and if you do Ohm's law with it, you'll actually find that what happens is light bulb initially has a huge inrush of current, and then once it heats up, its resistance rises a little bit. And this is why often when you turn a light bulb on, that's when they will burn out. There's that huge inrush of current, bump, thermally shocks it, and then the light bulb ends up burning out. So that's one thing that you can do. The other is a lot of great material science on this. There's a great site here that shows SEM images of how a light bulb burns out. And I think in the materials camp you've all seen the wonderful set of demonstrations you can do with a light bulb. So first of all, you can measure resistance just between this electrical contact and that electrical contact. You can measure resistance across it, compare big and small light bulbs. The other thing you can do is you've got a glass envelope. Well, what's the purpose of the glass envelope? It's basically so you keep the oxygen away from the filament. The coiled tungsten filament is the workhorse. Tungsten oxidizes very quickly in air, so you need this mixture of inert gases. So I think you've all seen the great bit where you can take a flame, put a flame on a light bulb if you're good at it. You can heat just a small area up. You'll see that the light bulb dimples in because the gases are at reduced pressure. If you preheat the whole light bulb, you can make it so the pressure is greater on the inside than the outside and get the bubble to go the other way. Ask your students why that happens. And then the other things you can do, and Andy and Debbie and others do a great job of this, you can cut the casing off the light bulb, get at the filament, look at that with a classroom microscope, measure the resistance of that, uncoil it, see that there's a huge length of wire associated with that. And the other thing you can do once you take the top of this off, you can plug in the light bulb, and this will last for maybe 1.5 seconds, and it goes poof, and there's some nice white tungsten oxide smoke that comes off of that. And there's lots to discuss on why you use the materials you do, resistance, engineering against oxidation. There's a huge amount of engineering that's gone into the light bulb, and what I like about it is it's really, really transparent. You can understand everything. And again, there's some great resources online, and this is a particularly good one. Okay, that's it. That's all I wanted to say today. I look forward to discussion on the board. So Ohm's law, I think, is a really simple way to show how predictive math can be. V is equal to IR. It works really well. Resistors you can make really accurately from wire. And altogether, this is a great way to teach energy transfer and where power comes and where it goes in a really transparent manner. And you can easily build a couple of weeks of really, really rich material around these ideas. And again, material science and how various materials play in the whole thing can really be a core integrating concept. That's it for now. Look forward to seeing you guys online. And keep that.